Okay, in this lesson, we're going to discuss something called transition state theory. This continues on from our lesson on collision theory, in that we now know that reactant molecules need to collide, and they need to collide in their proper orientation and with the proper kinetic energy. They need to have the right amount of energy in order to break those bonds. Transition state theory looks at what's happening very closely as the reactant molecules undergo a successful collision, and what takes place as they go from a reactant molecule to a product molecule. So the transition between reactant and product. And this is something we've never looked at before. Again, like I've said in the past, we sometimes consider a chemical reaction to be almost magic. We have reactants and then magically we have products. But there has to be a transition there, and that's what we want to look at in this particular lesson. So it's used to explain what happens after the reactant molecules collide successfully. It explains what happens as reactants become products. So let's take a quick look here at what really takes place two molecules as they approach each other. As two molecules start to run into each other, because they both contain electron shells, repulsive forces will take place, and they'll slow the molecules down. And so the molecules really have to be going pretty fast.
This is Garrett, phone call 01. This is Garrett. Please contact the office.
And so they've got to be moving fairly fast in order for the kinetic energy to be converted into the potential energy needed to break the bonds. And if they do this, if they have enough speed where the threshold energy, the kinetic energy it has, is equal to the activation energy, that's the potential energy needed to successfully collide. If this happens, then we will have a successful collision. The bond structures rearrange to form products only if we have enough potential energy. As the new molecules form, repulsive forces push them apart, and the kinetic energy increases in energy. In other words, they kick back out and away they go. So we've got kinetic energy of the reactants coming together. We've got this intermediate scenario where they're colliding and they're changing bonds, and then it turns back into kinetic energy as they kick away from each other. So let's take a look at a couple of diagrams that we're going to need to know in order to explain this. We call these potential energy diagrams, EP diagrams. Again, be very aware of the different axes and how we label them, because you will be asked to draw these on a test. In this case, we're looking again at reaction progress. We've seen reactions like this in the past, or diagrams like this, and the potential energy. We've seen them for exothermic and endothermic. Let me just review here what it's going to look like for exothermic. Remember, exothermic means that energy is given off. So our reactants start up here with a high potential energy. In the end, the products have a lower potential energy. Now, the difference between the potential energy diagrams we've done in the past and what I'm going to show you now is that we're going to connect these lines with a curve. And these curves represent what happens as the reaction goes. Just as before, if we've got a decrease in energy there, then we've got a negative delta H, and that's where we draw our delta H, and it's exothermic. But notice here, in this particular reaction, we needed a little bit of energy in order for the reaction to happen. And this little bit of energy is what we call our activation energy. That is the energy that's needed in order to break those bonds. So now our potential energy diagrams contain a little more information than they did in the past. They contain a little bump that represents that activation energy, that represents that energy needed in order for the reaction to happen. All right? One other term I'm going to add to this. Right at the very tip of the curve is where we have something that exists that's not a reactant and it's not a product. It's an in-between of reactant and product. And we don't know what to call this. It's not really a regular molecule. It's actually made up of the two molecules put together. We would call something like that a complex because it's made up of two molecules kind of stuck together in the process of making and breaking bonds. And so we call this thing that exists right at the peak of the curve the activated complex. And that's because it's a complex, it's made up of a reactant and product working together as they're working through, and it's activated in energy. It's at an elevated energy. Let's take a look at the example of the the endothermic reaction. So in this case, let's turn the whole thing around. I'm going to start down at the level that I left off with at the last one. I'm going to attempt to end off at the same level that I started with. And again, now you can see I've got the little bump. And in this case, you can see here going from this lower energy up, that I'm going to have my positive delta H. We've seen that in the first chapter. But this time, take a look. My activation energy is much greater because I need my reactant particles to have a lot more energy in order to get over the bump of the activated complex. All right? But I'm hoping you can see the symmetry in these two diagrams. If I have a forward reaction that is exothermic, and I then look at the reverse reaction that is endothermic, you can see there is definitely a mathematical relationship between the delta H, the activation energy for the forward reaction, and the activation energy for the reverse reaction. We could try to write down an equation for this, but we're going to have a lot of signs in it. There's going to be positives and negatives. And I think it's easier if when we do our calculations, that we keep these graphs in mind in order to come up with the proper calculation. So what we've looked at now is the curve, the transition between reactant and product, the fact that we need some energy in order for that reaction to go, called the activation energy, and right at the peak, at the highest stored energy, the highest potential energy, we have what is called the activated complex. So here we've got a diagram come out of a textbook, I think, represents an activated complex here. There's our delta H. Notice it's negative. This is an exothermic reaction. There's our activation energy, the energy needed to get it over the potential energy bump. This is where we need our kinetic energy. It's like rolling a ball over a hill. I need to give that ball enough kinetic energy to get up over the hill. If the ball does not have enough kinetic energy, it gets up to here, rolls back, then we have a failed reaction. But if I give that ball enough energy, which on our other graphs we call the threshold energy, if it makes it over the threshold, then we have a successful reaction that becomes a product. And here we've got one for an endothermic reaction. Again, see that larger activation energy. Again, imagine we're rolling a ball up the hill. These are reactants are going to need a lot of kinetic energy to collide and make it over to the product side. Again, there's our delta H, positive. I know we've got this written as being the opposite reaction, but this diagram is obviously not to scale because this should have been just as big as the previous one. All right, so let's take a look at some important things here. The difference between the energy of the reactants and the peak of the potential energy curve is what we call the activation energy. And here is how it affects the reaction rate. This is an important one right here. The higher the EA, the slower the reaction. So the greater that bump is, the slower the reaction will go. So the activation energy has a great effect on how quick the reaction goes. And also, we've seen the delta H before. It's the difference in energy between the reactants and products. I talked about the activated complex. It exists right at the peak. It's an unstable chemical entity that contains partially broken bonds and partially formed bonds. Represents the highest potential energy. We've got it's like stretching an elastic band and wondering if it's going to break. It's very, very unstable. It's a very high energy entity. formed only if the reactants collide with enough energy to overcome that activation energy barrier. Another term we're introducing here is the physical state, not necessarily solid, liquid, or gas, but that mixture complex, we call it the transition state. Right in that peak area, we say it's the transition state. Now, this type of question I'm really not a fan of, but some of the worksheets in the textbook does have this. You know, what might an activated complex look like for this particular thing? Well, we've got an H2 here and an O2. And I'm not concerned about the way you've drawn the bonds, whether you draw them as single or double bonds. But this type of thing is kind of a tricky thing to draw. And I'm not really that concerned about it, as long as it's got a little bit of logic with it. Here I'm drawing my oxygen, and I'm putting a dash between it to represent the fact that the bond is breaking. And what we could have is we could have hydrogen running into it on either side, perhaps doing that, where that bond is breaking as well. And we could even have the same over here. So what we have here is essentially, and you know what, if you were to draw this entire thing right here to represent what that activated complex looked like, then that would be good. But it doesn't even need to be that complex. That's why I'm not a fan of this type of a question. You could even have it drawn maybe as this. An oxygen runs into a hydrogen, and it forms something that isn't the complete reaction. So in other words, in this case, we're going to have a bond being broken here and being broken here, and a bond being formed here and formed here. And that's going to result in what we would see here as an OH. And then maybe that thing might run into another hydrogen. So again, don't worry about it. If you were to draw this, you'd get full marks. If you were to draw this particular thing, you'd get full marks here. All right? It's really a difficult thing to imagine what the activated complex looks like. But sometimes they'll ask you, and as long as it makes logical sense, it does not have to be complicated, you'll be awarded for that particular thing. So let's now take a look at what a catalyst does. We saw in the last lesson that the presence of a catalyst increases a reaction. I told you that, I had an analogy of where it's like a thug hanging onto a guy so that the other guy can lay a beating on him. I know it's not appropriate, but it kind of works out. So what does the catalyst then effectively do to our graph? Well, what it does, it simply changes the pathway. You'll notice I've put some bumps in here. Actually, I didn't. This graphic has some bumps in it. And that just represents that there might be some multiple steps that happen in there. Don't worry about it. If you were to draw on a test, if I were to ask you to draw a curve that represents a catalyzed reaction, and you were to simply make a curve that looks like that, that would be sufficient. The important part of this is that the curve for the catalyzed reaction is lower than the curve for the uncatalyzed reaction. All right? It effectively lowers the activation energy. There you can see it right there, lowers the activation energy. So what I'd like to do now is one last thing, is compare what we looked at in the last lesson with the graph that we looked at today. So what we have here are two graphs, and these are the two graphs we looked at in the last two lessons. This is the Maxwell-Boltzmann's distribution, and I'm going to draw it in here, right? Remember, it had a curve up here, and it kind of tailed away like that. And this represents how many atoms, or the collisions, that will result in a good reaction. And what we've seen today here is that we can have a reaction, like an exothermic reaction, that starts up here, has the activation energy, and drops down there. How do these two graphs relate to each other? Well, in order for me to do this, I'm going to rotate the first graph. I'm going to take the first graph and I'm going to rotate it up on its side this way so that we can compare the energy of collision with the potential energy needed to react. So that's what my next slide is going to do. Let's take a look here. There you can see I've rotated it. I'm going to put the curve back on the Maxwell-Boltzmann's distribution. There it is. It goes up and it trails away, just like so. All right. And I'm again going to put my reaction here. There is my starting reactant right here. I've got my product down here, and it's going to go up and down like that. So there again, you can see we've got an exothermic reaction. There's the delta H. I also have this EA that is needed in order for the reaction to have EA. Now remember, in order for a successful reaction to take place, I need particles that have the right EA. So I need everything, you'll notice here, so my energy here, I'm looking at the top of the peak, is what's needed for a reaction. That's my ET. So if the ET is the same as the EA, then I'm going to have all of these guys react. All right, there we've got a successful reaction right in there. But if I change now the reaction pathway, I'm going to drop it down here, I'm going to add a catalyst. So there's my catalyst. Notice for the catalyst, the delta H is the same, haven't changed anything, but the energy needed to react is now down there. This is the ET cat. All right, that's the ET with the catalyst. So what have we done effectively? We now have more of them that can react, and the reaction goes faster. All right, we have a greater fraction of successful collisions. All right, so that's how those two graphs relate with each other. Again, I can add one more little label on here. Down here is my EA cat. All right, EA cat, the activation energy of the catalyst. Again, it's brought it down. All right, so that's how my two graphs work together. That's how heating it up changes these numbers, but also changing the nature of the reactants. That's what this does, is change the, sorry, not the nature of the reactants, addition of a catalyst. That's how that affects that. Okay, so let's take a look at an example problem that you may encounter. So here we've got some CO reacting with NO2, and it's going to produce CO2 and NO. And I've given you some information. There's the delta H. It's positive, and therefore it is endothermic. And there's the EA. And we want to make a sketch of the graph. All right. And in part B, you can see we're going to label the EA, the delta H. We're going to draw a curve for the catalyzed reaction. So A, B, and C can be done all in one shot. So let's take a look at A, B, and C. Setting up my curve. Remember, this is reaction progress. All right. And this is the potential energy. We want to get the axes correct. We see that the delta H is positive. That means it's endothermic. So I'm going to do something like this. The EA is 143. It has to be larger because we need a little extra to get up there. Excellent. It wants us to label all of this information. And so all the way up there, I have the EA, and that is 143. From our starting point to the end, that's our delta H. That's 134. And it's asking to represent the catalyzed reaction. Catalyzed reaction will have a lower activation energy, so it's dipped down. That's the cat. All right. And it didn't ask for it, but I'll put it on here. Right at the tip, we've got our activated complex. All right. Excellent. That's a label of our potential energy curve. Propose a structure for the activated complex. Again, I think this is kind of a silly little procedure, but we could imagine perhaps that we have a CO something with the bond breaking. We've got an NO2, and perhaps that N is It's got the O hanging out there, and it's got the other O here, and maybe that bond is forming there. So again, in this case, we've got a bond breaking right there, and we've got a bond forming right there. And you know what? Like I said, I am not picky about this type of thing. That would get you full marks. It doesn't even need to be that complex. And last, for part E, this reaction can be reversed. Find the EA and the delta H of the reverse reactions. Well, this is where I was talking about needing an equation. And you don't need an equation. We can see it perfectly on the graph here. If I were to draw the EA for the reverse reaction in red right there, and I could call that EAR for EA reverse. So we can see here that there's a mathematical relationship. The delta H plus the EA reverse has got to equal the EA forward. And that's why I don't want you to worry about an equation. You can see it here. This delta H right here plus this EA reverse has to be equal to this number right here. So I can simply just make a mathematical truth out of this. It simply is 143 is equal to 134 plus EA reverse. 143 minus 134 equals EA reverse. And what does that get me? Oh, goodness gracious. That's 9, I believe, isn't it? 9, what are we doing for units? Kilojoules equals EA reverse. All right, 34 to 43 is 9. Okay? Very straightforward. Now at this point, your homework and practice doesn't come out of the textbook. It's on a worksheet, and you will get that worksheet, or you can get it offline. And here are the answers to the worksheet. Very similar type questions. All right? And in our next lesson, we're going to talk something about, there's 3 and there's 4. In our next lesson, we're going to talk something about reaction mechanisms, and that involves steps that exist in a reaction. Many reactions don't simply go from reaction to product. They go from reaction to product via many small reactions that take place very quickly. It's called a reaction mechanism.